Yes, there you go.
Okay.
So we now see your slides as their slides, and we can hear you fine. So if you're ready, please take us away.
Uh, Wait a second. Yes. Okay. Yeah. Whoops. First of all, thanks for the invitation. Um, and this is joint work with Arno Castells and Petra Wolf. And yeah, as in most temporal graph problems, what do we like to do? What have we heard today already in several occasions? We like to analyze problems that are easy on static graphs and analyze them on temporal graphs and look how the difficulty or the complexity changes. So what we looked into is connected components in temporal graphs. So first of all, the static case. We have in a directed graph, a strongly connected component is an exclusion maximal set of vertices that can pairwise reach each other. And for example, here in this static directed graph, these are the two strongly connected components. We can see it here on the left side. These three vertices can pairwise reach each other by going around this circle, starting from any point. And on the right side, these two vertices can pairwise reach each other by this bidirectional edge. And yeah, it is known that there is a unique partition of the vertex set into um, strongly connected components, and this partition can be found in linear time. So now, okay, again, very easy to solve problem on static graphs. What happens if we lift this concept to temporal graphs? Here we can define a connected component, in this case, a temporally connected component, as a set of vertices that can pairwise reach each other by strict temporal paths. And we heard the definition before, it's still here. Yeah, strict temporal path is just a sequence of consecutive time edges that are strictly increasing with respect to their time labels. So let's say we have here, well, let's be honest, it's a very degenerate temporal graph. We have a temporal graph with a single snapshot and, well, those edges here. And now finding a temporally connected component here is a bit more difficult. For example, we have the original, original, the connected components we saw before on the last slide for the static case. Um, we have this triangle over here, or this clique over here, and we have a clique over here, or a temporally connected component over here, because in both cases, all vertices can pairwise reach each other by always the direct edges. And the problem now with respect to the unique partition, this does not hold anymore on temporal graphs. Namely, for example, this edge or these two vertices over here also form a temporally connected component because, well, this vertex can reach this vertex can reach this vertex. But so we see we have like intersection of different temporally connected components. So finding a unique partition or finding a partition of the vertex set might be pretty hard, or uh, finding an optimal one in some way. And yeah, why is this different? Well, what is known? It is known that finding a large temporally connected component in the temporal graph is NP hard. And why is this? Well, it is because essentially finding a temporally connected component is equivalent to finding a clique in the reachability graph of the temporal graph. Um, what is the reachability graph of a temporal graph? Well, this is just a static auxiliary graph a directed static auxiliary graph having arcs from vertices u to v if and only if vertex u can reach vertex v by a strict temporal path. So for example, for this temporal graph, this here would be the reachability graph. And then we can see, okay, this triangle over here, it's a clique, so it is a temporally connected component. These two vertices to the right are a clique, and so a temporally connected component, and also these two diagonal vertices. And yeah, so the problem then of finding temporally connected components is called, well, TCC. And we just want to know for a given temporal graph and integer k, is there a temporally connected component of size at least k? As I mentioned, this is known to be NP hard, and based on the relation to clique, W1 hard when parameterized by the size of the sort TCC, even on temporal graphs of lifetime 1. So it gets pretty messy or pretty difficult to solve even on very restricted temporal graphs. And the question is now, what actually is the difference? I mean, we have a temporal graph, we have a reachability graph, and finding TCCs here corresponds to finding cliques in the reachability graph. And now if you look at the static case, why is it different? We can also define a concept of a reachability graph for a static graph as just the graph having arcs from vertices u to v, if and only if there is a path from u to v in the static graph. So this reachability graph would look like this for this static graph. And the question is like, okay, here again, a strongly connected component in the static graph is a bidirectional clique in the reachability graph. But for some reason, we can solve the latter thing, or on these reachability graphs, the problem in linear time. And the reason is that the reachability graph of a static graph is known to be transitive, meaning that if we have a path from A over B to C, then we also have the arc from A to C. And then finding, or what's the main reason? Yeah, the bidirectional cliques in such a transitive graphs have the property that each vertex is contained in exactly one maximal bidirectional clique, which makes it then easy to find the unique partition. And our idea was now, okay, can we use this property for our temporal setting? And to this end, we introduced two new temporal graph parameters based on the reachability graph of a temporal graph. Namely, first, we want to measure the distance with respect to vertex deletion to being transitive. So we want to know how many vertices do we have to remove to obtain a transitive graph. And it's important we first compute the reachability graph and then perform these modifications on the reachability graph. It is not a vertex deletion on the temporal graph and then obtaining a reachability graph that is transitive, but just we build this auxiliary graph first and just measure or define the parameters on this static graph, the static auxiliary graph. And yeah, so the second parameter we introduce is the arc modification distance to transitivity. So essentially, how many arcs do we have to remove or add to the reachability graph to make it transitive? And these two parameters have very nice properties, which are desirable for temporal graph parameters. Namely, first of all, these parameters can be small, they can be large, even if the underlying graph or the snapshots are very complicated or very complex, very dense, very sparse. Like, they do not limit the structure of the underlying graph or the snapshots. And what is maybe even more desirable is that these parameters are sensitive to reshuffling of the snapshots. I first explain what this is and then why it is desirable. So let's say we have here a temporal graph with 3 snapshots, and you don't have to verify this for yourself. This would be the reachability graph. And you can see this reachability graph is not transitive because like we are missing, we're having at least one intransitivity here from the bottom to the top one. And reshuffling of the snapshot now means like if I take the snapshot 2 and 3 and just flip them in the order of snapshots, so have like this temporal graph over here, then suddenly the reachability graph is a bidirectional clique, which means it is transitive. So changing the order of the snapshots, so varying the temporal graph itself changes the actual parameter value of these parameters. And well, why is this desirable for a temporal graph parameter? Well, essentially we want to capture how we want to really measure what a temporal graph acts like. And so a reshuffling of the snapshots should ideally change something in the parameter value if it really measures the temporality of the graph and not only on the snapshots and behaviors. Okay, so what did we do with these parameters? First observation for the vertex deletion and arc modification distance. One can easily see that the vertex deletion is at most 2 times the arc modification distance. It's like, give me an arc modification set. I take the endpoints of this arc modification set, remove them from the graph, and the rest is transitive. So the vertex deletion distance is never that big. And based on this, well, not based on this observation, but what we showed is that the problem can be solved. So finding temporally connected components can be done in 3 to the vertex deletion parameter times polynomial time. And based on this observation, this then also implies an FBT algorithm for the arc modification distance. And in contrast, we showed that, or additionally, we showed that for the arc modification distance, we can have a polynomial kernel, a cubic sized kernel, if one would give us an arc modification set. It is not completely clear how to get this set, so it is not a direct polynomial kernel, but if one would give us a set, we could compute a kernel. Yeah, and in the following, I will slightly talk about this FBT algorithm for the vertex deletion distance. So let's say this is our reachability graph of our temporal graph. And quick reminder, essentially what we want to do is we want to find bidirectional cliques in this reachability graph. So first step, what we do is we compute a transitivity modulator. So a set of vertices we have to remove to obtain a transitive graph. Let's check if this is true for this set. Okay, if we remove it, then we see we have like a bidirectional clique here, and to the right side, 2 strongly connected components, namely first the left 2 vertices and the right 2 vertices, both form 1 strongly connected component each. And we have like directed edges only from one side to the other. So, okay, we verified this vertex set is a transitivity modulator. And what we now do is like, we just iterate over each subset of this set S and just ask, okay, what is the largest temporally connected component? Or in this case, if we were looking just in the world of the bidirectional of the reachability graph, what is the largest strongly connected component that extends this given subset? So let's say we have these 2 blue vertices and we want to know what is the largest bidirectional clique containing exactly these 2 vertices and no other vertices from S. So we can remove all other vertices from S from this graph. And since we're looking for a bidirectional clique, we only keep those vertices from the bottom part that are bidirectionally connected to both these vertices. So for example, this vertex, I don't know if you see my cursor, I hope. You will see which vertices remain, namely these 3, and because all other vertices are not bidirectionally connected to both blue vertices on top. And then the bottom part is again a transitive graph because transitive graphs are closed under vertex deletion, which means that we can find a largest bidirectional clique or a largest strongly connected component in the bottom part in just linear time, and then extend it with the additional vertices on top, and so decide what is the largest bidirectional clique in this auxiliary graph, or going to where we came from, what is the largest temporally connected component of this temporal graph. So this leads us to the FPT running time. Essentially, the most part of the running time is just computing the actual vertex set. This is where the 3 to the power comes from. The remaining part only takes 2 to the vertex deletion parameter. And unfortunately, for this parameter, a polynomial kernel is unlikely. So there is no polynomial kernel for the vertex deletion distance plus some additional other parameters. And this is what motivated us to also look in this arc modification distance. I'm not going into details for this kernel for the arc modification distance. Instead, I want to show you some other limits of these parameters. Namely, if we're not looking for normal TCCs, or normally they are called open TCCs, but if we are looking for closed TCCs, these are temporally connected components for which the induced temporal graph is temporally connected. So intuitively, we take the set of vertices and we want that each pair of vertices can pairwise reach each other by only taking paths over vertices from the set S. So we are not allowed to leave the set S and come back in to achieve this realization. Wrong paper. This reachability. And so small example, let's say this is our temporal graph, and then the reachability graph of this graph would look like this. You don't have to verify it. And in this graph, well, the vertex set ACD is a temporally connected component because it's a bidirectional clique. So ADC is a temporally connected component, but it is not a closed temporally connected component because the only way to get from A to D is to go over the vertex B. So if you want to have A and D together in the same closed temporally connected component, then we also have to include B. But if we include B, we cannot include C because then these two are not bidirectionally connected. So just we can't take A and D together in one component. And yeah, here the main property that is a problem for closed components is like, again, each closed component, each closed TCC is an open TCC, so a bidirectional clique in the reachability graph, but the inverse does not hold anymore. So it's not an equivalence anymore. It's like, if I have a clique in the reachability graph, it is not necessarily a closed TCC. And if we then define a problem based on these closed components, where we ask for a closed component of size at least k, then it is again NP-hard, a known NP-hard and W1-hard problem. And we can essentially exploit this property that not all cliques are closed TCCs by extending the known result and showing that this hardness still holds even if both of our introduced parameters are just have just value 1. And I slightly sketch it in the next slide. So recall, closed TCCs are just the only temporal path connecting them should go in this vertex set. And what we do is like a self-reduction from this closed TCC, where we have, so this down here is the original temporal graph from the closed TCC instance itself, and we want to reduce it to the same problem again by just applying some connectivity gadget. Namely, we want to have a path on top here, which we would like to use to make each vertex from down here reachable from each other vertex from down here. And we do this by like adding some antenna vertices to all the vertices down here, and first connecting them to the left side of this upper connectivity path, and then also to the right side. So in this graph, we can now, I showed already, this would be the reachability graph. It's like a bidirectional clique on the bottom, including the vertex x2 and also these antenna vertices. And the only arc that is missing in this reachability graph is the arc back from x3 to x1. Like all other edges are there. It's nearly a complete bidirectional clique. And why is this? Well, okay, we can go from a vertex to its antenna vertex, to the start of this connectivity path, go over this path, and then leave towards each possible antenna vertex, and then from this antenna vertex then, or from this one, to the bottom vertex. So we always have paths from all vertex pairs to each other that go over this path on top here. And the thing now is, because x1 and x3 are not bidirectionally connected because x3 cannot reach x1, each temporally connected component can contain, each closed TCC can contain at most one of x1 and x3. And this means that with a dose of generality, we can assume x1 is not there. And if x1 is not there, no vertex from down here can reach x2, which means, well, we also can't exclude x2. And now if x1 and x2 are not in the closed component, then no vertex, or not sufficiently many vertices, can reach vertex x3. So we also can't exclude this include this vertex, which then leaves us with our original instance and these antenna vertices. And then we can essentially show that not sufficiently many vertices can reach these antenna vertices. So also those are also not contained in the closed component, which just leaves us with the original instance. So with this small connectivity gadget, we can just make the reachability graph very, very transitive, where we only have to add one arc or remove one vertex to obtain a transitive graph, while still preserving hardness results for the closed temporally connected component problem. And yeah, small outlook. From the positive side, all of our results hold for all versions of open TCC. Namely, if you consider strict or non-strict paths, directed or undirected temporal graphs. And it would be interesting to answer some open problems or some gaps in our results. So, for example, not all negative results work for all versions. For example, if you consider undirected temporal graphs with non-strict path, then it is not clear whether a polynomial kernel for the vertex deletion distance is possible. So this is the only case where a polynomial kernel could be possible for this parameter. And for our kernel, for the arc modification distance, as I mentioned, we need to be given an arc modification set. So it would be interesting to know if we can approximate such an arc modification set of small size efficiently. If this would be possible, then we immediately would get a polynomial kernel for this parameter, and we assume that maybe not constant factor, but like polynomial factor approximation for this set should be possible. Yeah, like it was also be interesting to see if other problems can be solved efficiently if these two new parameters are small. Also, what is about the closed TCC problem with respect to arc deletion? As I showed you, the reachability graph we built is like nearly a complete clique with just one arc missing. And if we only allow arc deletions in this reachability graph, then this parameter would be like linear in the whole input size with respect to in the reduction I showed you. So it is not clear whether maybe this parameter could still be useful for closed components. And one can now also consider like other parameters on temporal graphs towards transitive reachability, like really operations working on the temporal graph itself, like removing vertices from the temporal graph to then obtain a transitive reachability graph. It would be interesting to see if one can maybe, or if these parameters could be sufficiently smaller than the parameters on the reachability graph and still result into FPT algorithms. And finally, as a general goal, it would be nice to define or find useful parameters for temporal graphs that are sensitive to reshuffling of the snapshots. Yeah, that's all for me. Thanks for your attention. And if you have questions, comments, I'd like to hear them.
I think we have time for a question. If anybody has one online, either type it in the chat and I'll read it, or unmute yourself and shout. And while I'm pausing for that, seeing nothing urgent, I'll ask in the room. Questions?
I can ask.
Yeah, please.
Yes, so in static graph, people also look at like two connected or three connected or two edge connected, three edge connected components. Has there been any work in temporal graphs on such components? Or has nobody looked at this because even deciding whether there are two temporal paths, two disjoint temporal paths is already quite hard in temporal graphs?
I'm not sure if someone looked into this. I would assume there might be work on this, but as you mentioned, it's like it is all very, very hard for like finding a strongly connected component, or I think as Andrea will talk about in his upcoming talk, like unilateral components, like where you want to have like only a directed path of strongly connected components. So I would assume there is work on this. I'm not aware of right now, but yeah, it might get very hard, but it sounds interesting to look at.
Thanks.
Thank you. I have a bunch about parameters because I love parameters, but maybe I will contact you after the fact because I think my questions will probably not fit in 2 minutes. So if you don't mind getting contact afterwards, then I'll do that. Otherwise, let's thank Nils again.
Thanks for having me.